Okay, so last time we talked about nilpotent and solvable groups, and mostly about solvable groups. So these were sort of two different ways you could look at groups that are constructed out of abelian groups. Solvable groups are sort of the most general way, and then nilpotent groups were sort of, you put a little bit more restricted, but they had sort of a nicer structure theorem. But solvable groups are the ones we'll come back to when we study Galois theory. And so for now, that's all we're going to say about that. But yeah, and again, they'll come up after the midterm. So today, I just want to, I basically just do a few examples. Just illustrating some, not examples of solvable groups or nilpotent groups per se, though some will show up on the way. But just examples illustrating some of the things we've learned, and also illustrating some of the things we will use, we'll learn later. So that's the idea anyway. So let's start with just the last example I'll do where I classify, where I sort of prove there's no simple group of a certain order. So this is just a nice way to illustrate that there are, you can go further with clever arguments using Silof's theorems. Like there's much more you can do beyond what we've already done. And so this example sort of will illustrate that. So there's no simple group of order 3,675. Okay, so let me factor that for you. This is 3 times 5 squared times 7 squared. Or is that right? Yeah, 7 squared. Yeah, that looks right. Okay, so good. So why don't we first compute the number of Sylow 3 subgroups. So okay, well, it's gonna be 1 mod 3. And it will divide uh, 5 squared times 7 squared. Okay, and so, well, it's going to be, yeah, actually, I think probably we're going to need to do all of these. So let's do all of them. So Sylow 3 subgroups, so it's going to divide 5 squared times 7 squared. So 5 is congruent to 2 mod 3, and 7 is congruent to 2 mod 3. So like we're going to need to have a product of these two. So this is, we're going to have sorry, let me look at my notes to make sure. I'm a little bit worried I'm looking at the wrong number. Right, well, okay, good, sorry about that. I wanted to start with N7, not. Sorry. Okay, this will work better. Okay, so yeah, just like all these problems, you should start with all the Sylow P groups, but I mean, let me tell you ahead of time that N3 was going to be a dead end. What I meant to look at was N7. Okay, so let me try this again. So N7 is going to be what's congruent to 1 mod 7, and it divides 3 times 5 squared. And so, well, if N7 is equal to 1, we're done. Because then there's a normal subgroup of order 49. Otherwise, right, and so you can always sort of suppose the order of G is equal to 3675. So if N7 is equal to 1, well, then we're done because that's a normal subgroup, a non-trivial normal subgroup. Otherwise, we get N7 should be equal to 15. So that's the only other possibility that's, oh, can you guys not see my writing? So Sandra says she can't see anything after the factorization. Is that true for everybody else? Or can you see what I'm writing? Oh, I caught up now, okay. Has it been going, and for everyone else, has it been going in real time or? No, it hasn't, it's, okay. But it's, okay, I'm going to write something and tell me if it, okay, I just wrote something. Did you see that? Huh, okay, let me just try stopping the share and starting again. Now I've lost the chat window. Okay. I'm writing hello. Can you guys see that? Okay. Yeah. Let me know if it stops again. Sorry about that. Okay. So we have N7 is equal to 15. And so, well, let me fix let me fix a normal subgroup of order 15. So let me, or sorry, I see off segment subgroup. So let Q be a CLOF7 subgroup. And I'm going to look at the normalizer of G in Q. Okay, so this is a subgroup of G. And well, I can compute its size because I know that the normalizer of G, that's just the stabilizer, or sorry, the normalizer of Q, that's just the stabilizer of Q under the conjugation action. And I know sort of the conjugation action is sort of transitive on these 15 CLOF Q subgroups. So this is just, so we have the size of G divided by the size of the normalizer is equal to 15. So this is N7. So this is just like the orbit stabilizer theorem. Okay, and so good. So that means the order of normalizer of G of Q is equal to sort of all 5 times 7 squared. Okay, so and what I'm trying to do here actually, So I guess maybe I should have said this before. And somehow I'm playing around with subgroups because I want to produce a subgroup of sort of large enough index that I can. So the way this argument is going to work is I'm eventually going to produce a subgroup of sort of small enough index that the permutation representation on its cosets has to have a kernel. So this is sort of one of the strategies we saw way back at the start is like, if you can sort of find sort of a permutation representation that has sort of a non-trivial kernel, but sort of the permutation representation is sort of, so if you can find a permutation representation of sort of small enough size, then it sort of has to have a kernel just by like Lagrange's theorem. So like if G acts transitively on a set with 5 elements, well, like, for example, that would have to have a like, use different ways to say it. Like if G acted transitively on a set with 5 if G acts on a set with 5 elements, then, and as long as it acts non-trivially, you're going to get a sort of map from G to the symmetric group on 5 elements. But sort of like, for example, G has an element of order 7, and sort of the symmetric group on 5 elements doesn't have an element of order 7, so that map couldn't be injective. So this is a way we used at least once before, and probably used it on the homework. And then the first example we did, where there are different ways where if you can get a permutation representation on sort of a small enough set, then you can just sort of derive basic contradictions using the order. So that's sort of where we're going. So what I'm trying to do here is I'm going to try and bootstrap off of sort of the Syloff-7 subgroup and something we know about it to produce sort of a permutation representation on a sufficiently small set. So here, and we're getting a permutation representation on a set of size 15. That's too big. Like S15, like 15 factorial is much bigger than this number. And so there's no way we can sort of use that to get a contradiction. So we need to cut this down again. So we're going to need to bootstrap off of this normalizer to produce a an even larger subgroup. But we have ways to do that. So we're going to do something sort of clever. So let's get a look at the now we're going to look at this group NG of Q. And this has a unique Syloff-5 subgroup. And just because in the options for the number of Syloff-5 subgroups are 1, 7, or 49, those are the divisors of 7 square, and only one is despite the congruence condition. Okay, so let me call that subgroup P. Okay, and so this is normal in this normalizer of G. So P is a normal subgroup of the normalizer of Q. And so another way we can write that is that the normalizer in G of P, so let me say it this way, the normalizer of G in Q is a subgroup of the normalizer in G of P. So saying that you have P as a normal subgroup of this just means sort of when if I conjugate P by any element here, I sort of land back at P. So that's saying this is a subgroup of the normalizer of P. So this gives me a way to sort of go from this normal so I had this normalizer of Q. So I started with a Syloff subgroup, the Syloff-P subgroup, a Syloff-7 subgroup. I looked at its normalizer, and then now I'm taking now I found a normal subgroup of that. And so sort of the normalizer, and this gives me a way to make a bigger group than the normalizer in G of Q. Okay, so good. Well, okay, so by so I want to sort of look at this group P now. So I want to study the normalizer of P. Well, now I have P is a 5 group. Well, it's inside of so we start off sort of inside the subgroup, but in particular, it's a five group that lives in G. And so it's contained in, so here, literally P has order 5 because it was a CLOF 5 subgroup of this thing that had order 5 times 7 squared. And so it's contained in a CLOF 5 group. G. So the order of P star is equal to 5 squared. Okay, and we've seen that P star is okay. So we've seen that P star is what have we seen? Sorry, we've seen that P star that's sort of a group of order. Well, any square of a prime. So in particular, 5 squared is abelian. Okay, so in particular, like in an abelian group, like in conjugation of anything else, anything by anything else is trivial. Is in conjugation, the conjugation actually is trivial. So in particular, we get that P star, it normalizes P. So this group of order 5 squared normalizes this group of order 5, i.e. P star is contained in the normalizer of G of P. So P was this group of order 5 that we sort of constructed as a sort of CLO 5 subgroup of the normalizer of a group of order 7, or sort of order 49. And then so we took this group of order 5, and then we said, well, okay, I mean, it's a subgroup of G, and we know any group of order a power of 5 is contained in sort of a maximal group of order a power of 5 in G. So a CLOF 5 subgroup of G. So it's contained in the subgroup of order 25. But this subgroup of order 25 is an abelian group because any group of order 25 is abelian. So in fact, like what we get out of this is that P star normalizes P, and so it's contained in the normalizer. So we now have sort of 2 important facts. So we have that the normalizer of G in G of Q is a subgroup of the normalizer in G of P, and that we have sort of P star is a subgroup of the normalizer in G of P. Okay, so this first one was because P was a normal subgroup of this normalizer, because it's the unique CLOF 5 subgroup. And the second one, just because sort of P is contained in P star and P star is abelian. Okay, so this means, well, the size of the normalizer in G of Q was 5 times 7 squared. So this divides the order of the normalizer in G of P. And P star had order 5 squared, so this divides the order of the normalizer of G of P. And so, okay, so we got 5 squared times 7 squared divides the order of the normalizer of G of P. Okay, but like look at our, so in other words, the index of this subgroup is either 3 or 1. So when you divide the order of G by this, you're just left with 3. So maybe this was really everything and it was over the size, or maybe not. Then you get maybe the normalizer G of P is everything. Okay, so if it's 1, then the normalizer of G of P is equal to G, so P is a normal subgroup. So that's another way of saying you're a normal subgroup, is just that your normalizer is the whole group. Otherwise, you get a map that's non-trivial to S3 just by action on cosets. For G mod NG. Another way to say this is just by sort of action by conjugation. So the orbit of P under conjugation. So this is, as a G set, this is isomorphic to the orbit of G under conjugation. So these are equivalent statements. By the way, I mean, you get a set of size 3 with a non-trivial, with an action of G, a non-trivial action of G. So you get a non-trivial map from G to S3. So here by non-trivial, I just mean it doesn't send everything to the identity element. Okay, but then sort of the kernel of this map is a non-trivial normal subgroup. Because I mean, the size of G is much larger than the size of S3, which was 6. So that sort of concludes our proof that there was a normal subgroup. Just to recap, I mean, we started with like the most basic trick of all of just computing sort of CLOF P subgroups, and we saw, well, okay, if there's one CLOF 7 subgroup, we're done. And then the only other possibility is there are 15. So let's see what happens to there are 15. Then we sort of fixed the CLOF P subgroup, CLOF 7 group Q. So this had order 49. And we said, let's look at the normalizer of that. And we know the order is 15, just the number of CLOF 7 subgroups. And so we get the order of this normalizer is 5 times 7 squared. And the strategy now was we wanted to sort of find an even bigger group until we could sort of make this permutation argument. We wanted to sort of find a group of sufficiently small index so that this permutation argument could work. And so we sort of took this thing and we found, well, we took its unique CLOF 5 subgroup. So we took a normal subgroup in here, and then we just use like this trivial fact that like, so if you have a subgroup like H and a normal subgroup M inside of H, then the normalizer of M contains H. So like if you're sort of trying to find a bigger subgroup containing this, you can just find sort of a normal subgroup inside of it and take its normalizer in all of G. Like that gives you a way to produce a bigger subgroup. So that's a potentially bigger subgroup, and so that's what we'd said. So we sort of looked at this unique CLOF 5 subgroup in here, and we said, look at its normalizer. And then we used the fact that sort of this 5 group is contained in a CLOF 5 group, and that's sort of G. So that gave us sort of a way to add some extra elements, to find some extra elements in the normalizer that we hadn't already seen. I'm just using that sort of this CLOF 5 subgroup of G has order 25 and is abelian. So P sort of was so it's contained in a normalizer of P. Okay, and then we just did basic Lagrange theorem to deduce that the order of this group is very large, is at least 5 squared times 7 squared. So its index is very small, is either 3 or 1. If it's 1, then this is a normal subgroup. Or sorry, if it's 1, then sort of P was a normal subgroup of order 5. Otherwise, we got this sort of permutation representation on the cosets or on the conjugates of P that sort of is to a very small symmetric group. And so then that has to have sort of some non-trivial kernel. So that's outlining the argument. And it's not, yeah. Anyway, just to illustrate that you can really you can take these ideas that we've seen so far in simple examples of like different ways you can use T-loss theorems and just arguments using normalizers and so on to produce a normal subgroup. Like you can really sort of take them much further than we have. We're not going to take them any further, but you can. And so maybe it's interesting to do that. And this gives you some insight into sort of why you might be able to prove much stronger theorems than what we've proved, to like why sort of, I mean, somehow, like, it's nice to see that there are some sort of non-trivial techniques. There's some techniques we haven't exhausted yet. If you're going to believe that you can prove like these very strong theorems like Feit-Thompson theorem or like classification of simple groups. Okay, so that's that example. So are there any questions about that example? The normalizer, if it's index 3, yes, that's a good point. Yeah, that's a great point. So if it's index 3, then since 3 is the smallest prime dividing the order of the group, then you could also deduce in that way that that the normalizer itself was a normal subgroup. Yeah, great, thank you. And so in that case, I mean, yeah, great. So in that case, I guess in this case, the normalizer itself will actually be the kernel of this map. Okay, great. Yeah, good. Any other questions? Okay, so let's move on. So the last thing I wanted to do in this unit is talk a little bit more about, to do one more example of constructing a simple group. Okay, so if you think about this problem of classifying simple groups, well, what do you need to do? Like, well, you need to do two things. Like, first, you need to like build as many simple groups as possible. Like, you need to sort of find simple groups, and then you need to show those are the only ones. Like, you need to show you couldn't get some other simple group. So, like, how can you do that? Like, how do you show those aren't the only ones? Well, like, it's arguments of the sort of kind we've been giving. Like we've seen sort of lots of examples like this where we sort of pick some order and we say, okay, there's no simple group for that order. What you sort of will find if you keep on doing this kind of thing is like, there are certain orders where you can sort of break out all of the tricks in the book and like all the CLOS subgroups, you can sort of try everything you know how to do. And like, you still won't, like, you do that and like, you'll deduce a bunch of things about sort of such a group, but you won't deduce it has a normal subgroup. And so like, sort of if you sort of give yourself some number and you sort of try and do this, then and you sort of try all your tricks and you say, okay, I can't I can't deduce there's a normal subgroup still, then like you ask yourself, is there a simple group of that order? But then it becomes a completely different problem. Like you have to then construct a simple group. And that's like, showing something exists is very different than showing something doesn't exist. Like the kinds of techniques you can use and what you can rule out. And so, yeah, I just wanted to, so I want to do one example where, one more example where sort of we construct a group and we show it is simple. And so actually in the end, like once you construct a group, the kinds of tools you use to show it is simple are maybe not so different. Like sort of looking at Celoff groups, the subgroups is a good idea, and so on. But good. Okay, so let me. Yeah, so let me do this. So here's the example. So maybe I'll just set up some preliminaries and then we'll take a break and then we'll finish it. So the group, the GL3 of F2 is simple. So let me just make a remark. That if you did your homework carefully, won't be a surprise to you, but I haven't looked at it yet, so I don't know how many people did their homework carefully or didn't do it carefully last week. Actually, was it last week or was it this week? No, okay, so did you guys have a problem? For the homework due on Tuesday, was there a problem about like GL2 and PGL2? Yeah, okay, good. So it was the, okay, so then I can say this. So is the remark, I mean, so GLN of F2 is equal to PGLN of F2. And this is also equal to PSLN of F2. But for other primes, this isn't true. So for other primes, so like for odd primes, for P odd, GLN of FP, so ejects onto PGLN of FP, and then this contains PSLN as a normal subgroup of index well, I started to be this depends on sort of P and N. Okay, so for certain P and N, this index will be trivial, or this index will be 1, but in general, it won't be index 1. So like if you're looking to to generalize this example, you should look at PSLN, so the projective special linear group of FP, and even not just FP, but sort of other finite fields. So I'll talk about other finite fields in a minute. Just because, I mean, so GLN has an obvious normal subgroup given by its center. So when its center, so you did this problem on last homework, and you saw for GL2 of FP, the center was just sort of the scalar, like the matrices that just had like the same scalar along the diagonal. Well, when P is 2, like the only non-zero scalar is 1. So that's just identity matrix. But when P is larger than 2, like then there are scalars that are not 1. And so then there are sort of non-trivial matrices in the center. So in GLN of FP is never going to be, it's never going to be simple because, like, except for maybe if n is equal to 2, because it contains a non-trivial center. But so you can just take the quotient by it and you get sort of this PGLN. But then this also sort of might not be, normal because sort of it has the subgroup PSLN, which sort of might be a proper normal subgroup. So it sort of depends on what are the determinants you can get of a scalar matrix. So this is, so, and on this homework, this was like when you did for P not equal to 2 and n equals to 2, you get index 2 subgroup here. And that's because sort of if you look at sort of the determinants of a scalar matrix, a 2 by 2 scalar matrix, well, it's either going to be, it's going to be a square in FP. And so the squares is square in FP star, and so the squares in FP star are an index 2 subgroup. Okay, so, well, hopefully that's something all of you noticed, and if not, well, that's okay, now you know it. But anyway, there's a subtlety at P equals 2. I didn't tell the grader about the subtlety either, so maybe if you didn't notice, maybe the grader didn't notice the P equals 2. So maybe you'll be lucky. You'll find out. Okay, so good. So anyway, this is just a remark. I mean, I haven't said anything about how we show that GL3 F2 is simple yet, but just like I wanted to point out that if you want to sort of then try and generalize this statement and show sort of many other, and put this sort of into a family of simple groups, like the right thing to do would be to look at the projective special linear group. So this is sort of matrices of determinant 1 modulo the scalar matrices of determinant 1. Okay. Good. So that's one thing. So how do we do this? Well, and maybe let's first just compute the order of GL3 of F2. And actually, maybe I'll just ask, can someone, so you guys thought about this for GL2, so hopefully you have an idea in your head of how you might do this for a larger n if you haven't thought of it before. But so can anyone tell me what the order of this group is? Okay, good. So I just got it in chat. So it's p cubed minus 1 times p cubed minus p times p cubed minus p squared. That is correct. Can someone besides Sandra, who just wrote it in chat, can someone else explain this, like explain where these numbers are coming from to me? Okay, thanks. Yeah, great. Yeah, great, thank you. So just to repeat that, So for a 3x3 matrix to have determinant not equal to 0, well, it's the same as just saying the column vectors are independent, the columns are linearly independent. And so you can just pick them, you can just pick the columns one at a time, sort of left to right. So the first column, you sort of just pick, and you want to sort of do something that can be completed to a linearly independent set of vectors. So your only restriction is you can't pick the 0 vector. So you get sort of p cubed choices. That's sort of all possible column vectors in FP. So because there are sort of three entries in your column vector, and each of those is an FP. So sort of each of those has p choices, so you get p cubed. But you have to exclude one. You have to exclude one of those choices, because if you chose 0 for every entry, that would be the 0 vector, and there's no way that's going to be part of a linearly independent set. And then the second column, this is all vectors, the 0 vector. So the second column, you have to pick something that's linearly independent from the first one. So you start off with p cubed possibilities, which is all vectors. But then just in saying that you're picking a vector that's linearly independent of the first vector just means it can't be a scalar multiple of the first vector. So there are sort of p scalar multiples of the first vector. These are the scalar multiples of the first vector. The first column. And so good. And then for the third column, you get p cubed again minus p squared. So this p cubed is again all vectors, and then p squared, these are linear combinations of the first two vectors. So to get something that's linearly independent, just remove all linear combinations of the first two vectors, and sort of then that resulting set will be linearly independent. So in linear combinations of the first two vectors, I mean, that really includes like the 0 vector, or multiples of the first vector, or multiples of the second vector, but also then sort of, and so sort of somehow you're still covering all your bases from before, but by saying this. Okay, and then you just, to get your sort of total choice for the matrix, you just multiply these three numbers together. And so this is a fun little trick, and you should remember it. And knowing this number is useful, and yeah, and you can, like from this, you can also sort of then deduce the size of like SL3, for example. You just now divide by p minus 1. And there's lots of other sort of related things you do. And this formula sort of generalizes completely to GLN of FP. So you just start with p to the n minus 1, then take p to the n minus p, then p to the n minus p squared, and so on. So this is a completely general thing. Great. So thank you, both of you. So good. So in this case, that means the order of GL3 of F2, that's 2 squared minus 1 times, so 2 cubed minus 1 times 2 squared minus 1, 2 cubed minus 2, sorry, I get turned around, times 2 cubed minus 2 squared. So that's 7, 8 minus 1 is 7, good, times 6 times 4. So that's equal to 2 cubed times 3 times 7 is equal to 168. Okay, so that's the size of the simple group we're constructing. So we're constructing a simple group of order 168. And I think you already know how many, well, depending on if you did this first problem on the last homework you, I think then know how many elements of order 7 this group has, or something like this. One of the problems was about, but anyway, we won't use that. But anyway, you already know something about this group. Well, okay, let's pause here. We'll take, and we don't need that much. The proof doesn't take that much time. So, well, let's take we'll take a long break. Why not? Sort of end of a unit. So we'll take a 9-minute break, and we'll come back at 1:20. and then we'll actually prove that this group is simple. Yeah, sure. Okay, so we'll get back to this. So we wanted to prove that this group GL3 of F2 is simple. So there's a group of order 168. And so, well, part of the proof is going to look a little bit like the proof that the alternating group is simple. So let me, let me recall what, and so what did we do when we proved the alternating group was simple? Well, we did this inductive argument. And like one of the main things that made that inductive argument run was the alternating group, like AN, well, it's inside the symmetric group SN, so it has a natural action on sort of the set of elements 1 through n. And then we used sort of that then we looked at the stabilizers of all the different elements, and that action is faithful, was sort of the main point. So that means sort of like the intersection of the stabilizers of all the elements was the trivial group. And so that was sort of an important observation that let this argument, that actually like let this inductive step run. So we're going to use a similar thing here. So by definition, GL3 of F2 has a faithful action on the set F2 cubed. So this is column vectors of height 3. With entries in F2. So, okay, so it depends on what you mean. Depends on how you define GL3, whether this is really by definition or not, but like sort of, and you probably the best way to define GL3 of F2 is this is just sort of automorphisms as F2 of an F2 vector space of height 3 column vectors. If you think of these as matrices, so this is sort of 3 by 3 matrices with non-zero determinant. And the action of a matrix on a vector is just given by matrix multiplication. So A is a 3 by 3 matrix, V is a 3 by 1 matrix. So A times V is another 3 by 1 matrix. So, okay, well, it depends on how you want to encode these things, but this is sort of one way to encode this. And okay, but sort of, okay, by definition, this is faithful. Let me say that in a slightly different way, though. So actually, let me ask you a question. What are the orbits of GL3 of F2 acting on F2 cubed? So let me say an easier question. Give me one orbit of this action. Let me refine this even further. So Well, okay, so there's an answer in the chat. Let me ask you one more question that will sort of make you see that this answer is not quite right, but is almost there. What is, so there's one point that is fixed by this action. What point is that? Yes, so 0 is fixed by this action because the 0 vector, A times 0 is equal to 0 for any matrix A. So one orbit is 0. Okay, and so then why is it and so then I claim that the other orbit is just everything else except 0. So why is this the other orbit? Let me, if I do A times 1, 0, 0, what is that? Like, what is that vector? Well, but in hitting, yeah, so. Right, and that argument that you just gave needs a little bit of expansion, but someone just typed in the chat that this is the first column of A. Good. So, okay, this is the first column of A, but in our argument, we already saw sort of the first column of A can be any sort of non-zero vector. I mean, we already saw this when we were counting, like counting how many elements were in GL2 of F2. Like we said, we'll start with the first column, it can be any non-zero vector. So that means the orbit of this point 1, 0, 0 contains all of the non-zero vectors. So that's a quick way to see that this is the other orbit. Okay, good. So in fact, I claim, well, the action of GL3 F2 on sort of this second orbit of non-zero vectors is transitive. Is faithful. Sorry, I keep on saying transitive when I mean faithful. So that just means sort of the map from GL3 of F2 into sort of the permutation of the set is injective. Or equivalently, that the intersection of the stabilizers is trivial. Well, and that follows immediately. I knew the action on all of F2 cubed was faithful by definition. And then, well, everything, like the action's like as far as possible from faithful on this first orbit, like the kernel of action on this orbit is just the whole group. So that means sort of if it's going to be faithful, it still also has to be faithful on this other orbit. That's sort of a fancy way to argue. A less fancy way to argue would just mean like if you have something in the kernel of this action, then it fixes the three standard basis vectors. So that means all of its columns are its columns are the three standard basis vectors. So if in the kernel, so if A is in the kernel, then A times E1 is equal to E1, A times E2 is equal to E2, and A times E3 is equal to E3. So A is the identity matrix. And there's nothing special about E1, like the three standard basis vectors here. If you took any basis vectors, if you took any basis, then this sort of same argument would work. Okay, so good. So this is a faithful action. So this means, so what does this mean? So this means the intersection of sort of all the stabilizers this is just the identity element. So this is exactly like what we had for the alternating group when we were doing this proof of the simplicity of the alternating group, where the intersection of the stabilizers of all sort of the numbers 1 through n was just the trivial subgroup. Okay, so but we won't use the statement quite the same way, but and this is a useful statement. Let's look at the stabilizer for a second. So in the stabilizer of x, and this action is faithful and it's also transitive because it's just a single orbit. So the stabilizer of x has index 7. So for any x, the stabilizer of x has index 7 in GL3, just by the orbit stabilizer theorem. In the orbit, the 7 is the number of vectors in F2 cubed minus 0. Okay, so this is the orbit stabilizer theorem. And we can, so it has size, sorry, what was the order of this group? 168. So I guess this has size 24. That looks right. Right, so this was 2 cubed times 3. Okay, good. And we could check this by hand too. And you can write down what the stabilizer is for sort of a specific point. The stabilizer of the first basis vector, so just the bit vector 1, 0, 0. Well, this is just everything that has first column 1, 0, 0. So the second column can be anything. The third column can be anything, sort of as long as this is in GL2 or GL3. So this is in GL3. Sort of if the vectors are linearly independent, so the 3 columns are linearly independent still. So again, and you can sort of do this computation another way. You can just do what we did before. So there are, well, this middle, we've prescribed what the first column has to be, but the middle column, we still have 2 cubed minus 2 choices. And then the last column, we still have 2 cubed minus 4 choices, minus 2 squared choices. So this is 6 times 4. So this is another way you can check this. You can sort of really write down explicitly what this subgroup is. Okay. So good. So anyway, so and this we won't use this, but this is somehow useful. No, and then well, now the stabilizer of any other, like it's useful to sort of see this picture that this is just matrices you can write down. And the stabilizer of any other element is sort of just a conjugate of this, like you sort of, when stabilizers are like stabilizers for a transitive action are conjugate. So sort of the stabilizer of any other point is just sort of some conjugate of this, which of course makes sense because if you just sort of took that point to be the first vector in a basis, then like you just conjugate the matrices, like conjugation sort of corresponds to change of basis. And sort of there's some other basis where you really have just these matrices. So anyway, it's sort of maybe useful to think about different ways you can say the same thing here, just to get your head wrapped around what's going on. But all we actually need is that, let me highlight what we actually needed. So we needed just the intersection of the stabilizers is trivial, and that if I will sort of fix a point, then the stabilizer has index 7. Okay, so I mean, how is this going to be useful? So let me I'm going to make the rest of the argument. I'm going to make the next step of the argument. So, and then I'm going to go back and we're going to look at something about the structure of this group again. So I'm going to suppose now H is a normal subgroup of GL2, GL3 of F2. Okay, well, and let me write, so then if H is not trivial, let me say it this way. So if H is contained in the stabilizer of this first basis vector, then H is trivial. Why? Well, because then H is contained in sort of the stabilizer of X for every vector. I'll write V instead of X. Just because the stabilizer for all these different elements are conjugate. So it's the same, the exact same argument we did sort of for the alternating group. The stabilizer of all these different elements are conjugate, and all these different non-zero vectors are conjugate. And H is preserved under conjugation. So it's sort of preserved, it's in all of these stabilizers. So it's in the intersection. Sorry, this is a subgroup. And it will be automatically normal, but. So then H is in the kernel of the action on F3, F2 cubed minus 0. And so H is trivial. It's contained in the intersection of all these stabilizers, which we saw was trivial. Okay, so H is not in the stabilizer of E1. So H, is then so H times the stabilizer of E1, well, has to be equal to all of GL3 of F2. Just because the stabilizer has index 7. So like this group is either index 1 or like this is sort of has, and this is a subgroup because H is normal. So if you take a normal subgroup, multiply anybody in a group, this is a subgroup. So there's a subgroup and sort of, well, it's either index 7 or index 1. And like it's only going to be index 7 if H is contained in the stabilizer of E1. So this is actually equal to everything. Okay, so good. So we get the 7. So in particular, we get that 7 has to divide the order of H. Okay, so good. So let's look at the Celoff 7 subgroups of H. Okay, well, we're going to assume H is not equal to G because we're trying to find we're trying to find a sort of, we're trying to prove GL3 of F2 is simple. So we're looking for a normal subgroup that's not the trivial group or all of G. So we're assuming H is not equal to G. So then, well, the order of H is equal to, so what was the order of a group that we started with? I always start 2 cubed times 3 times 7. So it's well, 7 times 2 squared times 3, or 7 times 2 times 2 cubed times 3, or sorry, 3 cubed, or it's equal to 7 times 2 times 3, or it's equal to 7 times 3, or 7 times 2. Hopefully I hit everything. Okay, that's probably everything. If I didn't hit everything, just sort of extend the argument I'm about to say will still work. So only, or it's, oh, it could be 7. Yeah, good. Okay, good. Okay, so then we get sort of the number of CLOF7 subgroups for H is equal to 2 cubed or 1. So it's either equal to 8 or 1. Okay, so right, so may come back in a second and I'll show you it has to be 8. Or yeah, no, I'm probably going to show you right now it has to be 8. One second. H is a normal subgroup. Right, so yeah, sorry. So I think I can say it. So, and if it was 1, then, oh yeah, great. So great. I mean, so we have it would be bad. Yeah, sorry, I got lost about what we were trying to do. I mean, we're trying to prove this group is simple, and it would be bad for us if there were only one CLOF7 subgroup of H, because like a CLOF7 subgroup of H, well, H is a normal subgroup. So like G sort of preserves subgroups of H by conjugation. And if there's just one CLOF7 subgroup of H, then like it's preserved by conjugation of all of G. So like if there's one CLOF7 subgroup of H, which is a normal subgroup, then there's only one CLOF7 subgroup of all of G. So then this would actually be a normal subgroup of our whole group, GL3 of F2. And so that's sort of, okay. And yeah, so somehow that would be bad. I mean, I guess we're trying to rule out this possibility. Okay, so we want to rule out this possibility. So let me just say, yeah, sorry, I don't have the same amount. I'm running a little bit out of time, so let me just say in quickly. So construct CLOF7 subgroups of GL3 of F2 by sort of constructing a degree 3 field extension of F2. So, well, we're going to talk more about this later, so maybe we'll come back to this exercise after the midterm, just sort of, but anyway, you can construct a degree 3 field extension of F2 call it F8, and look at F8 cross acting on F8, which is can be viewed as a three-dimensional F2 vector space. So I claim well, F8 cross is going to be a group of order 7, and it's going to be acting on this two-dimensional vector space. So you can if you fix a basis of this three-dimensional vector space, then you'll get an embedding of this group of order 7. And so using this embedding, you can construct more than one CELO 7 subgroup of G. Okay, so that was the point. And if there was just one CELO 7 subgroup of H, then in fact there'd only be one CELO subgroup of all of G, because a 7 subgroup of all of G, because H is normal in G. And so if we can produce more than one CELO 7 subgroup, then we rule out that case and we conclude that H has size 7 times 2 cubed. Okay. Okay, and so it's 1:46, so I guess I stop here to conclude, to finish. Now think about you're going to look at CELO 2 subgroups. But let me, I guess leave that as an exercise. And maybe we'll come back to this part of it. So I might do this, I might finish this just at the start of class next week. And then this part we'll come back to after the midterm at some point. We'll look at this again. Yeah, sorry, I'm a couple minutes over, so let me stop and I'll stick around if there are any questions.